Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover simple machines. This content was produced with AI assistance and reviewed by a human instructor. We're starting with a short history of the simple machines. From the digging stick to the law of the lever. The oldest simple machines predate writing. Stone hand axes, wedges, appear in the archaeological record long before any treatise about them. The earliest examples from Kokisale, West Turkana, Kenya, have been dated to about 1.76 million years ago. Balance scales using a first-class lever appear in Egypt by about 5000 BC, and the shadouf, a counterweighted lever for lifting water, is attested in Mesopotamia by about 3000 BC. The wheel and axle appears on potter's wheels in Mesopotamia by about 3500 BC and on carts by about 3200 BC. Figure 1.1. A shadouf stands at the bank of the Nile, a long wooden pole balanced on a clay fulcrum post, with a heavy stone counterweight lashed to its short end and a leather bucket hanging from its long end over the water below. The counterweight does most of the lifting work, so a single worker can raise hundreds of liters of water per hour with far less muscular effort than lifting directly. The first-class lever in everyday practice, circa 3000 BC. What changed in the 3rd century BC was not the machines, but the mathematics. Archimedes of Syracuse produced the first surviving rigorous proof of the law of the lever in his treatise on the equilibrium of planes, proving that magnitudes are in equilibrium at distances inversely proportional to their weights. Pappus of Alexandria records Archimedes' boast, "Give me a place to stand, and I shall move the earth." Plutarch tells the companion story. At King Hiero II's request, Archimedes is said to have moved a fully loaded ship single-handed by means of a compound pulley, a public demonstration of the mathematics he had just proved. Figure 1.2. A harbour scene. Archimedes stands alone on the stone quay of Syracuse, pulling a single rope that threads through a cascading series of pulleys attached to a large merchant ship, which begins to slide across the water toward him. Each additional pulley in the compound block and tackle halves the force required at the rope. With enough pulleys, the effort of one man equals the weight of a fully laden vessel, a public proof of mechanical advantage before King Hiero II's court. The same Archimedes is credited with the Archimedes screw, a helical pump for raising water. Whether he invented it or refined an Egyptian device he encountered in Alexandria is disputed. Screw pumps may predate him by centuries. What is not disputed is that screw pumps still drain polders in the Netherlands and lift effluent in modern wastewater plants. The device carried his name across the Roman Empire. Figure 1.3. An Archimedes screw at a waste facility plant in cross-section. A tight helical blade wound around a central steel shaft inside a close-fitting cylindrical housing, set at a shallow angle with its lower opening submerged in a river channel. As the shaft rotates, each pocket of water trapped between successive turns of the helix is carried upward and discharged at the top. The geometry of the spiral converts continuous rotary motion into a steady upward flow with no valves, no pistons, and no intermittent lifting. Hero of Alexandria and the Canonical 5. About 3 centuries after Archimedes, Hero of Alexandria compiled the Hellenistic engineering tradition into a treatise called the Mechanica. The Greek original is lost. The work survives only in a 9th century Arabic translation, with fragments preserved by Pappus. Book 2 of the Mechanica opens with the canonical list of 5 powers: the windlass, the lever, the pulley, the wedge, and the endless screw, by which any weight may be moved by any given force. Hero wrote that these powers are all derived from one natural principle, though they are very different in form. That single statement, 5 machines, 1 principle, is the seed of all modern statics. Stevin, Galileo, and the 6th machine. Hero's list omitted the inclined plane. The Greeks understood ramps as a practical aid. The pyramids could not have been built without them. But a passive slope did not match their idea of a machine with moving parts. As late as 1826, Carl von Langsdorff still wrote that an inclined plane is no more a machine than is the slope of a mountain. Two Renaissance figures changed this. Simon Stevin, a Flemish engineer working for Prince Moritz of Nassau, published The Principles of the Art of Weighing in 1586. He derived the equilibrium condition on an inclined plane using a thought experiment. A closed loop of identical spheres draped over two inclines of different slopes, which he called the clootcrans. He showed geometrically that the effective gravitational force along an incline is proportional to its vertical height, independent of its length. Stevin was so pleased that he printed the wreath of spheres on the title page of every book he wrote, beneath the motto, "What looks like a wonder is not a wonder." Figure 1.4. Two inclined planes of unequal slope share a common apex. A closed wreath of identical spheres loops over both surfaces and hangs freely below their lower edges, forming a loop that cannot rotate without implying perpetual motion. Because the loop is in equilibrium, the number of spheres on each slope must balance the component of gravity along that slope. Stevin's clootcrans proved that force along an incline is proportional to height divided by length, the sine of the angle. Galileo Galilei, while holding the chair of mathematics at Padua, wrote a set of lecture notes called On Mechanics, composed around 1593 to 1602. In On Mechanics, Galileo treated all 6 machines under a single principle. The same amount of work is required to lift a load through a given height, regardless of which machine is used. He famously warned that machines do not cheat nature. They transform energy, they do not create it. With Galileo, the canonical 6, lever, wheel and axle, pulley, inclined plane, wedge and screw, were complete, and the underlying conservation principle was explicit. Figure 1.5. 6 labeled panels show the classical simple machines arranged side by side. A crowbar prying up a stone for the lever, a wooden doorknob and spindle for the wheel and axle, a single rope and bucket pulley, a loading dock ramp for the inclined plane, an axe splitting a log for the wedge, and a wood screw driven into a plank for the screw. This panel serves as the visual catalogue for this video book, a picture of each machine in everyday use before we derive the mathematics behind it. Look around your environment right now and identify, by name, at least one example of each of the 6 simple machines. For at least 3 of them, decide whether the machine is multiplying force, multiplying distance, or merely changing direction. That wraps up a short history of the simple machines. Next up, Section 2, Work, Mechanical Advantage and Efficiency. If you found this helpful, like and subscribe, and support the channel.